Exercise 12F. This is from the Oxford Applications and Interpretation SL textbook. Question 1. An open cylinder has a volume of 400 centimetre cubed. The radius of the base is 5 centimetres and the height is 8 centimetres. A. Show that pi r squared h equals 400. Well, there's our cylinder. The area of the base, this alone is pi r squared, and we know that the volume of the cylinder, therefore, is pi r squared times h. So that's pi r squared h. They told us that the volume is 400, therefore pi r squared h equals 400. B, write down an expression for the surface area A of the open cylinder. Well, the surface area is this part here, which is here, and also the piece that's wrapped around there, and we can flatten that out. This distance is 2 pi r, that's the circumference of a circle, so that's the 2 pi r, and there's the h. So the areas of both these two would be pi r squared, which is that one, and 2 pi r times h. So that's the expression there for the surface area. C, show that this can be written A equals pi r squared plus 800 on r. So what I've done is I've changed this. I've rewritten this by dividing by r and multiplying by r. I can do that, just multiply the top and bottom by r. So that became 2 pi r squared h on r. So that term is now 2 pi r squared h on r. This remains the same. We know that pi r squared h is 400 because we've got that back here. So we can then substitute 400 in for that, and we've got pi r squared plus 800 on r. So that's okay. D, sketch the graph of that. Well, just use your GDC, and there it is there. That's actually from the back of the book. Okay, now, next one, find the minimum area and the value of r when this occurs. The minimum area is found by taking the derivative of a and equating it to 0. So we've got a equals that. Now that comes from here or here. And we're going to rewrite it before we take the derivative. We want to put that in, use the indice form. So we've got pi r squared plus 800 times r to the minus 1. The derivative is 2 pi r minus 800 r to the minus 2. And that resolves into r equals 5.03. Now, when r equals 5.03, we put it back into this one here, and we get 239 centimetres squared. Verify that it is a minimum point. We'll use the GDC, and by observation, it's a minimum. Question 2, the total surface area of a closed cylinder is 5,000 centimetres squared. Find the dimensions of the cylinder that maximise its volume and state this maximum volume. Verify that it is a maximum point. The surface area of a closed cylinder is 2 pi r squared plus 2 pi r h. Okay, that's defined there. It's got the top and the bottom, so that's 2 circles, and that's 2 pi r squared, and it's got the curved surface, which is 2 pi r times the height. And we know that's 5,000, so we derive all this, and we get h equals that. So I've got that in terms there. Find the dimension of the cylinder and state this maximum. Okay, so we have that. We know h in terms of r. We know this formula, which is the volume of a cylinder. We substitute 1 into 2, and we get V equals 5,000 r minus 2 pi r cubed. So we put all of that in for h in here. So we substitute all that for h, and we get that. And we take the derivative of this, and it becomes that. Okay, the maximum is that dV dr equals 0. So we substitute 0 in for dV dr, and we get that. We resolve it to r equals 16.28675. which is 16.3 centimetres to 3 significant figures. So when r equals that, we're going to use 1 over here. We're going to put r in and find h. Okay, so we put r in. We substitute 16.28675 into here and here. And we find a value of h, which is 32.5735, which is 32.6 centimetres to 3 significant figures. Okay, they're also asking for the maximum volume, maximise its volume. So we substitute r, which is 16.28675, into this formula here, and h at 32.5735. So we've got that, and we get 27,144.582, which is, to 3 significant figures, 27,100 centimetres cubed. Question 3, a vegetable garden is in the shape of a rectangle. The garden is surrounded by 100 metres of fencing. A, if the width of the garden is x metres, that's x, find an expression for the length. So let's call that x, and well, that's x, and this is y. Let y equal the length. The perimeter is 100. They told us that because the garden is surrounded by 100 metres of fencing, so all of that must equal 100. Well, we know that length would be 2 of those and 2 of those, so 2x plus 2y equals 100, or x plus y equals 50. So the length y is equal to 50 minus x, because y would just bring the x to the other side there, or minus x from both sides, and you've got y equals 50 minus x. B, show that the area of the garden is this. Well, we know that the area is x times y, so we substitute 1, the y is 50 minus x, into 2. So we substitute for this y, we're going to replace it with 50 minus x. We've got x times 50 minus x meters squared. C, find dA dx. We expand 3. We're going to expand this first, and we get 50x minus x squared, and we take the derivative of that, and that's 50 minus 2x. D, find the maximum area and the dimensions of the garden at this point. Okay, the maximum area is when dA dx equals 0, so 0 equals 50 minus 2x. We've taken it from here, so therefore x must equal 25. When x is 25, y is 25, so it's effectively a square. Therefore, the maximum area is 25 times 25, which is 625, and the width is 25, and the length is 25. 4, a cone has radius r centimetres and height 18 minus r centimetres. Find the maximum volume of the cone and the values for the radius and the height that give this volume. That's our formula for the volume of a cone. And when they tell us that h equals 18 minus r, it says that there, the height is 18 minus r. So we've got the height in terms of r. So we substitute this h into here, and we've got 1/3 pi r squared times 18 minus r. We expand it, and we get that. The maximum volume occurs at where the derivative equals 0. So the derivative equals that. Okay, I took the derivative of this, and that equals that. We say where that equals 0 will give us the maximum volume, and so that gives us r equals 12. The radius is 12. Now we substitute 12 into 1 back into here, and we can find the height. So the height is 6. And the maximum volume then, we can use the volume formula, which is this one here. It's 1/3 pi times r squared. We said r was 12, and h is 6, and we get 905 centimetres cubed through significant figures. 5, a rectangular piece of card measures 20 centimetres by 24 centimetres. Equal squares of side x centimetres are cut out of each corner. That's represented here. So all of that length there is 20 centimetres. All of this is 24. And we've cut these squares, which are x by x, from every corner. The rest of the card is folded out to make a box. We can then fold it to make this. Find the volume of the box in terms of x. Well, we know that this length now, if that's 20 centimetres from there to there, and we've got 2 x's, so it's going to be 20 minus 2x would be this length. And that's shown here, 20 minus 2x. If all of this is 24, and we've got 2 x's cut out, if we just want to know this part, that's 24 minus 2x. The volume of a box is going to be the length times the width times the height when it's folded. This will help. There, 24 minus 2x times 20 minus 2x times the height. We multiply all that out. Now the back of the book just stops here. I've expanded it to here, which we need for the next part anyway, but it looks like you could stop here. Just the length times the width times the height. B, find the value of x for which the volume is a maximum, and find the maximum volume. Well, the maximum volume is when dV dx equals 0. The volume is this. Okay, we determined that in A. The derivative of that is this. We equate it to 0, and we solve for x. I use the GDC polynomial tools, and I got 2 answers for x. So the volume is a max at that. Now I've excluded this one because if you put, if it was 11, and we said this side is 20 minus 2 times 11, that would give a negative dimension. Well, that's not possible, so we exclude 11.045176, and we take this one, which the 3 significant figures is 3.62. We need to now find the volume at x equals 3.62, and so I've gone ahead and used this one, because we've got volume in terms of x, and we're using our 3.621490, substituted that for x here, and we've got 774 centimetres cubed as 3 significant figures. Question 6, a closed cylinder has a volume of 300 centimetres cubed. If the radius of the base is r centimetres and the height is h, find an expression for the volume. We know the volume of a cylinder is pi r squared h, and they've told us it's 300, the volume's 300, so 300 equals pi r squared h. Find an expression for the total surface area in terms of r. Well, remember, this is a closed cylinder, so it has a top and a bottom, which we call the lid, and a base. So that's how we can work out the surface area. This green area here is the curved surface there. The total surface area is 2 of those and 1 of those. So that's 2 times pi r squared, because we know the area of that is pi r squared, and the area of this is the circumference times the height, 2 pi r times h. And so that's our expression for the surface area. C, find the minimum surface area and the values of r and h that give this area. Well, from this one here, we can get h in terms of r. So we've got h equals 300 on pi r squared. And we substitute 3 into 2. Okay, we want to substitute this h into an expression using just r. And we have that for ourselves here. Total surface area is 2 pi r squared plus 2 pi r times 300 on pi r squared. So I've substituted that in there for h. And that becomes 2 pi r squared plus 600 on r. Okay, let's rewrite 4 into this form here because it's easier to take the derivative. So we've got the total surface area is 2 pi r squared plus 600 times r to the minus 1, which is exactly what that is, just rewritten. So the derivative of a with respect to r is 4 pi r minus 600 r to the minus 2. I took the derivative of that. Now the minimum surface area is when that equals 0. So let's use the GDC to confirm this is a minimum. Okay. And we've confirmed it's a minimum. We put 0 equals that, and we find r equals 3.63 to 3 significant figures. To find the minimum surface area, we substitute that value of r into 4, into this, and we can find the total surface area there, which will be the minimum surface area, because we're using the minimum r, and we get 248.082072, or 248 centimetres squared, to 3 significant figures. Question 7, the profit P that a firm makes per day, right, P is in dollars, can be modelled by the function, this function here, where N represents the number of goods sold per day. Find the maximum profit and the value of N when this occurs. Well, that's just repeated to that. We've called that equation 1. Use the GDC to confirm it has a maximum, or look at the coefficient of the N squared term. And since it is negative, it clearly has a maximum. So we know it is a maximum. dP dN is this. I've taken the derivative of that. The maximum profit occurs when dP dN equals 0. 0 equals that. Therefore, N equals 180.978261, which is very close to 181. And it's the number of goods, has to be an integer, so we take 181. To determine the maximum profit, substitute 2 into 1. So we've got 181. Again, it has to be an integer because it's the number of goods sold per day. We're not selling half of a goods. Okay, and we substitute 181 back into 1 into this. And we've got $2,700.29. So keep it like that, 2 decimal places, because it's money. Question 8, a company's weekly profit in dollars in relation to the number of units sold each week, X, can be multiplied by the function, this function. Find the maximum profit and the value of X when this occurs. Well, that's our function. We call that 1. Confirm there is a maximum using GDC, or notice coefficient of X squared term is negative. So that's a negative coefficient, so it must be a maximum. Maximum profit is when the derivative of 1 is 0. Use the notation Px to represent the profit in terms of X. So this got Fx there. I've changed it back to Px as per previous question. So dP dx equals minus 1.8x plus 52. I've just taken the derivative of that. The maximum profit is at dP dx equals 0. So we put 0 in for that, and we find that x is 28.9 to 3 significant figures. However, x is an integer. It is either 28 or 29. Use GDC to confirm that x is 29 will give a higher profit than x is 28. Therefore, x is 29. This is similar to the previous one, but I didn't focus on it too much. But you need to know that this is units sold. We can't have half a unit. Similarly, the previous one. So you have to take a whole number. And I've chosen 29 here because that would give a higher profit than 28. To find the maximum profit, substitute 2 into 1. And we get the maximum profit is $391.1. Well, it is money, so maximum profit is $391.10.